Hey students, I got a couple questions from this chapter 13, number 48, so I thought I would go ahead and make a video of it. It starts here with a process which is known as enriching in uranium using gas diffusion. In fact, there it is right there. And let me begin, before I even start the problem, with printing the equation that we really need, which is going to be this equation. And before I just kind of jump right into it, I guess I should say two comments about it. This equation is what we're going to need, comes from here. And so the physics part of it maybe is worth doing some review. And then the applied part of it, maybe I should just say that's what we're going to do. So it's kind of a judgment call. If you're focusing a little more on the physics, maybe what I'll say is becoming important. But for most of you, being in the biological sciences, probably the end result is the useful one, to know how fast molecules are moving. And that's what this is about here. And so if you have, a container filled with a gas, and we ask, what's the difference between a gas that is hot and cold, we would say, well, the hot one, the molecules are moving around. They have more what? More speed, more momentum, more kinetic energy. I mean, when we say they are moving faster or they have more motion, what do we mean by that? And it happens to do with kinetic energy. It's based on the fundamental idea of what we call the equipotential energy theorem. In other words, if I have just some objects that can only move, that means the only form of energy they can have is kinetic energy. And so if I say, okay, what kind of energy they could have, and if they could only have kinetic energy, you might say, well, they have a certain amount of kinetic energy because they can move in the x direction, but they also have the freedom to move in the y direction, and they also have the freedom to move in the z direction. And so we like to use this phrase, 3 degrees of freedom. That is, these molecules can move, and of course movement involves kinetic energy. Their kinetic energy can be distributed in 3 different, I'll call it, well, the best word is degrees of freedom. 3 different places the energy can go. A movement associated along the x direction, a movement associated along the y direction, and a movement associated with the z direction. And the equal partition energy theorem says thermal energy is random in nature, that it will distribute itself equally into each of the degrees of freedom. So wherever the energy can go, which in this case is 3 different locations, it would have this much energy associated with the x motion, and this much associated with the y motion, and this much associated with the z direction. And so their kinetic energy is then associated with its temperature, its thermal energy. And if you put this thinking together, you can see that this first term becomes 1/2 m, and then you have the velocity squared in the x direction, the velocity squared in the y direction, and the velocity squared in the z direction. And this is just Pythagorean's theorem, or what we call the 3-dimensional version of Pythagorean theorem. And so this is just velocity squared. The whole velocity, because the velocity would be made out of an x part and a y part and a z part. Now, to be a little more accurate, we should probably then say that this random bouncing means that some molecules at one moment would be going fast and others at that same moment would be going slow, but they'd bump into each other, and as they bump into each other, the slow ones may go fast and the fast ones may go slow, but they have some kind of average. And so if we borrow the mathematical symbol of the bar over the top for average, we could really say that we have the average of the squares. And so the square root of this is then the square root of the average of the squares. For short, instead of square root, we say the root, and instead of average, we say mean, and then, of course, S for squares. And so we would call this the RMS value squared, because this right here is the average of the squares. It is the square roots. Oh, well, I guess without the square, it's the square root. And so we square them, then we average them, that's the mean, and then we take the square root. So the RMS value. And that's what this equation gives us. Now, you can see the other side of the equation, the 3 degrees of freedom, just means that this equation becomes 3 times 1/2 times Boltzmann's constant times the temperature. And this is probably the best way to learn it in terms of fundamental physics. That look at your degrees of freedom and then write out all the energies, because there could be more. But for a simple problem that is just made out of solid objects that are bouncing, you don't have any like potential energies or any other place for the energy to go. And so we don't have anything more than 3 degrees of freedom. We don't have 6 or 7 or 8. But you can imagine that many molecules, especially the atmosphere, which is mostly nitrogen, would have diatomic, because we know that nitrogen is this triple bond diatomic molecule. And so for something like this, the energy can go to other places besides translational motion. It can rotate and have rotational energy, or it can stretch, have vibrational motion. But again, I'm getting off of track and focusing a little bit way past what this problem is trying to do, which is just trying to get you to not necessarily do fundamental physics, but to use the result of fundamental physics. So you can see that if we cancel off the half on each side, move the m to the other side, and take the square root, s, on the left-hand side, we would get just the RMS. And then over here, we would get the square root of 3 times Boltzmann's constant times the temperature over the mass. So I hope these first 7.5 minutes didn't waste too much of your time. That was just kind of a mini lecture of how the physics works out. I should probably then just say, for you guys who want to apply the physics, especially apply it to biology, you will be fine enough just to know that the motion of the molecules, if we don't have anything too complex that has vibrations or rotations, is connected then to the temperature. And this is that mathematical equation. And this is the equation that we want for this problem. Let's finally start the problem now that we're over 8 minutes into the video here. It says there are 2 important isotopes of uranium. Uranium-235 and uranium-238. These isotopes are nearly identically chemically, but they have different atomic masses. Only uranium-235 is very useful in nuclear reactions. So the goal of the scientist, the engineer here, is to separate the uranium-238 from the 235. One of these techniques is to realize, and I'll come back here to the fundamental physics, if you have a bunch of gas particles at the same temperature, but because they have different masses, they're going to have different velocities. And so if you look at the atmosphere, one of the smallest or least massive molecules in our atmosphere is H2O. So it's going to have some of the highest velocities for the same temperature. So you kind of, in the room I'm right now, it's probably roughly 22 degrees Celsius, which is 295 Kelvin. So if I put that into here and put the mass of the water molecules that are bumping around, I could find out their RMS speed. But if I replace that with, say, carbon dioxide, which has a molar mass of 44, where this was 18, and so this is more than double, I'm going to find for the same temperature, which means the same kinetic energy, a different speed. So things that are more massive, which in our problem, the uranium-238 are going to be moving slower compared to the uranium-235. And so if I have some kind of barrier, a diffuse barrier, the ones that go faster are more likely to get through the barrier. And so if I have little microscopic holes and I fill it with gas, the faster moving ones diffuse faster. So past this wall, I will have a larger concentration of the lighter molecules, which in this case would be the uranium-235. And if I did it again and again and again and again, and especially in this case, because their mass isn't much different, I would have to do it a lot for a long time just to kind of get just a hair amount. And so the process they're looking at was actually the first process done during World War II in the Tennessee Valley Authority. That's how they separated out uranium-235 from uranium-238. And that's where this problem is going down here. It says, let's see, one of the techniques is to use gas diffusion, and it is based upon the different average speed of the uranium hexafluoride. And so it has uranium and kind of in a three-dimensional, and so along the x-axis there is a fluorine on both sides, and along the z-axis there's a fluorine on each side, and up and down there's a fluorine. And so you have uranium and stuck to 6 fluorine atoms. And if one of the uraniums is 235, it's going to be moving a hair faster than uranium-238 because of what we were talking about earlier, that for the same temperature, things with big mass go slow, or the other way around, things with small mass go fast. Okay? And there's not going to be much difference, which is why, like they said, it's going to take really a lot of effort. And that's what this says. It says the molar mass of uranium hexafluoride with a 235 and a 238 differ, and they give you the amount. So I guess we don't even have to look up the atomic mass of fluorine. It says, what is the ratio of their velocities? All right. So if I write this equation twice, so I'll say, what is the RMS of the uranium-235? This would be the square root of 3 times Boltzmann's constant times the temperature divided by the mass of the molecule that is uranium-235. So that'll be the one that goes faster because it's lighter in mass. And if I write that same equation but apply it to uranium-238, it would look almost the same, except I would have the mass of the uranium-238 molecule. And so this ratio of their speed would be what I get when I divide this equation by this, or this equation by this equation. And so the velocity, RMS, of 235 divided by the velocity of 238 would be the square root of, and maybe I'll save a little paperwork by just saying that over that, because what I want to do is take advantage of algebra here and say if I have the numerator and the denominator as a square root, I can just write a square root over the whole fraction. So this would be this number in the numerator and this number in the denominator. And I think it's going to take quite a bit of work for this problem. And so I'll put page 1 and then page 2. But this ratio, velocity to velocity, And it'd be okay. I'll just kind of drop the RMS and put 235, 238. And here's where I'm going to notice that there is a 3 and a Boltzmann constant, and for that same temperature. So in other words, I have them in a container at the same temperature bouncing around. But again, the 235 is going to go faster, just a little bit. So in other words, this ratio is going to be a little greater than 1. I would then get, and I'll just do the square root. Looks like I have 1 over M235 over 1 over M238. Well, again, that's a compound fraction, so let me take advantage of the compound fraction by flip and multiply. So that takes the mass of 238 on the top and the mass of 235 on the bottom. And so this ratio becomes, and now I can come back to the question, 238 is 352 grams per mole. And the mass of 235 is 349 grams per mole. And so I finally get the answer to A, which is this ratio. So let's see, 352 divided by 349, and taking its square roots is 1.0043. And I'll just stop there, but it does match what I was saying, that this ratio is going to be greater than 1, but not by much. These barely go faster, which is why you can see I keep emphasizing that, because step C, it says, do your answers in this problem imply that this technique may be very difficult? And yes. Separating them by their speed is not simple. Actually, separating them by their mass is not simple. And so putting them in a centrifuge is not easy. Putting them in a gas diffusion chamber is not easy. In fact, the hardest step of making atomic weapons is this step. Putting them in a mass spectrometer is not easy. And so all the techniques that we have, and we can't do it chemically because they're both uranium, all of these techniques are extremely difficult. And then, to be honest, the rest of the part of making an atomic bomb is actually pretty easy. So if you're willing to put in the time and energy and resources, and actually it's pretty straightforward. It just takes time, money, and, well, time and money, because the money and the time give you the resources, and then you can build a bomb. All right, so part B, I think, says something like this one. And this is probably where I'm getting the most questions, because I looked at the way the author does the solution, and it's not wrong. It's not the way I would have done it. So let me do it a little different way than your author. It says, at what temperature would their average velocities differ by only 1 meter per second? So these things are going really fast, and to have the lighter one move a little bit faster, only 1 meter per second, what temperature is that? How warm do you have to get this? And you can see it's pretty warm. So we've got to trap this gas in a very warm container. So all of our parts have to be operating at this very high temperature. It means they can't melt. So I guess I would do this. So the velocity of the 235, which would be the fast-moving one, minus the velocity of the 238, that's the little slower one. Let me set that equal to 1 meter per second. That's the kind of the thinking behind this. And then I'll just, again, use this equation. So this would be the square root of 3 times Boltzmann's constant times the temperature over the mass of 235. Then let me subtract the square root. of 3 times Boltzmann's constant times the temperature of the mass of the 238. And again, that's supposed to equal 1. That's kind of the design here. What temperature is that? Now, if it will be okay, I do have some math here I need to do. I'm trying to solve for temperature, but at least what I am saying is these would be the same temperature. So if you kind of let me separate this out, so I'll have like a square root of 3 times Boltzmann's constant over the mass, and then the square root of T. And then I will subtract that from the square root of 3 times Boltzmann's constant over the mass. And I should put 238 here and 235 here. I'm square root of temperature. It allows me to get the temperature by factoring it out. And what I would be left with is the square root of 3 Boltzmann's constant over the mass of 235 minus the square root of 3 times Boltzmann's constant over the mass of 238. And those numbers I know. And so I can get a number here and then bring it over and then eventually solve for the temperature. And maybe I'll do this one by itself here. Let's just do the square root of 3 times Boltzmann's constant times the mass of uranium-235. Because here's where I'll need to be a little careful. Let me put in Boltzmann's constant first. And kind of remind you of something I didn't really do in part A. And that is, technically, this is the mass of one molecule. But if you remember, as I was doing part B, I put in the mass of a whole mole. This is their molar mass. In fact, I didn't really say whether these were grams or atomic mass units. You see, if I put them in as grams, then I'm really implying this is the mass of one mole. And that's probably what most of you were thinking if you were watching the video at that point, is that, oh, he's putting in the molar mass. He's putting in the mass per grams, not the mass of one molecule. And you're right, I did that. Because it's a ratio, though, the ratio of the masses of their molar mass is the same as the individual molecules. And so even though you probably were thinking of this as grams, I was putting them in my head as atomic mass units, because that's what an atomic mass unit is that the same number for a whole mole, when you think of them in grams, is the same number of atomic mass units when you're thinking of one molecule. So I really was thinking one molecule here in atomic mass units. Now, here's the reason I say that, is over here, to get my temperature to come out in Kelvin, because Boltzmann's constant is in joules and Kelvin, this mass needs to be in kilograms, and it really needs to be one molecule. So what I'm saying here is I need to put in the 349, thinking of it as an AMU, an atomic mass unit, and then converting an atomic mass unit into a kilogram. And that's what I'll need to do in my calculation here. Okay, so this whole number, I guess, would come out to be 3 times 1.38 times 10 to the negative 23. Then I will divide it by 349 and also divide it by 1.67 times 10 to the negative 27. Oh, and then the square root. Let me not forget that last step. So we're looking at about an 8.428 here for that term. Now, this other one would be using 352 atomic mass units. And so maybe to save myself a little bit of calculator work, I'll just go up to that line and just copy it and say, okay, here is the 3 times 1.38 times 10 to the minus 3 and divided by, and this time I'm going to go 352. And then, of course, we still have the conversion to atomic mass units. So you can see we get a little bit smaller number, and of course we also have the square root of that. And so this is minus 8.392. When we subtract these two. And so, again, saving me some calculator work, I'll take that and subtract it with that one. And we are looking at a really small number, 0.03599. All right, well, like I said, it's going to take quite a bit of time and a lot of pages. Let me then write what I have so far. And so I have the square root of the temperature equals the difference of these square roots, which is this 0.03599, and that's all supposed to equal 1. So, in other words, 1 divided by this last answer is the square root of the temperature. So the square root of the temperature is about a 27.78, and so if I square both sides, we are looking at about 772 Kelvin, or if you like, let me subtract 273, and we're looking at about 500, which is quite warm, degrees Celsius. In fact, it's higher than the melting point of many of your softer metals, but not as high as steel or aluminum. No, I think that's higher than aluminum. But this can handle steel. But it's warm, very, very warm. And that's going to add to the difficulty. I don't know what temperature they actually operated at. Obviously, the higher you want it, the better, because the faster that difference in speed is, and the better the diffusion rate would get. And so you have a combination of deciding, when it comes to the engineering, how warm do you treat these gases, and then, how many times do you run it through the diffuser? And, how much do you, what we would call enriching it? Because if you just wanted to use uranium-235 for peaceful reasons, like a nuclear reactor, that's much, much easier than, say, weapons grade. But even that's misleading, weapons grade. You can make a bomb at less than weapons grade. So I'm not exactly sure why we call it weapons grade, to be honest. But, yeah, making a bomb way below weapons grade, but much more enriched than just for peaceful purposes. So you have two levels, and countries do that. Some countries just do it for peaceful reasons, and that's as far as they go. Other countries will go a little further and use it for weapons. And I think, I've already answered here that, yeah, this is going to be difficult. Not impossible. In fact, really not technologically that unreasonably hard to do. Just takes time and resources. All right. Well, I hope I didn't talk too much, but I hope I gave you a little more on the background, and hopefully it was useful. Take care.